Okay, so let me go ahead and get rid of this. And take a look at this guy right here. Again, so let's talk about the test. The test is Monday and Tuesday. I'll tell you quite a bit more about that tomorrow. I'll show you roughly what the format will be. You can expect about 20 problems the first day and about 20 problems the second day. I've taken the test several times. I think time-wise, if you've been practicing, if you know what we're doing, for example, on the first day, there's a bunch of factoring problems. If you know how to factor the stuff that we've talked about in class, it should be pretty darn quick. If you don't, you could stare at some of those all day. And if you don't know the difference of cubes formulas or the sum of cubes formula, it doesn't matter how long you look at it, you're not going to get it. Okay, so some of those things just flat have to be memorized, practiced, so that you recognize them when you see them. Okay, so time-wise, you should be fine. The review problems that you should be looking at tonight and over the weekend, those are pretty representative. If you know how to do the stuff that we've talked about in the notes in class, and have asked questions on the assignments that we've been given and stuff like that, you should be in pretty good shape. There should be stuff on there that should be easy, and there might be a couple things on there that will be a little bit challenging, but definitely doable. Okay, and I, that's why we're doing it over 2 days. I want to give you plenty of time. I want to make sure that we're all on the same page, so we can really judge, what your skills are at this point. Okay, don't be nervous or anything, but do work hard. It would be in your best interest to have looked over and done some of the review assignment tomorrow before you come to class. All right? Because if you come tomorrow and don't have any questions, haven't looked at it or anything, if you don't know what you don't know and what you need to ask questions about, tomorrow's not going to be as productive as it could be. Okay? All right, everybody clear on that? Okay. All right. So this section is on graphically representing data. And there are some things where we just, literally, graph some points and stuff like that. So in your own words, how would we graph the point -4, 3? So we got a little xy plane here. How would you graph the point -4, 3? Miranda? Okay, so this means left 4, and then what? And then up 3, okay? So from this point right here, from the center point right there, which we call the origin, okay, so we call that center point the origin. That's like the starting point for everything. We're going to go left 4, so 1, 2, 3, 4, and then we're going to go up 3. So this is the point right there. Happens to be in quadrant 2. Remember, we number them 1 and then 2. We go in a counterclockwise fashion, okay? So those are the quadrants. So we've got the origin there and the point there. And then the next question is, and think back to a week or two ago when we were kind of thinking like mathematicians and why somebody would develop something like this. Why do we do it that way? Why don't we go down 4 and then right 3? Yeah. Okay, because the x is this coordinate and y is that coordinate. X is horizontal, y is vertical. Well, why do we do it that way? Because it's convention. It's convention. Now, somebody could have, if hundreds of years ago they would have said, hey, you know what? Let's have this be the y and this be the x. That's what we'd be doing today. Okay? It's just convention. Okay, now the problem with conventions is if you don't like them, that's tough. You could try and make your own convention. You could have started maybe in 7th or 8th grade and said, hey, you know what? I'm going to do y here and I'm going to do x here. And I'm going to see how many people I can get to agree with me. Maybe you could have got a few people in your own class to buy into that, but do you think you could change the entire mathematical community and the way people do things? Probably not, okay? So some things you just need to buy into, okay? X is horizontal. There may have been a good reason for that. Maybe they just started plotting in one dimension first, okay? And we usually use x, so they called that the x-axis. And then they said, hey, wait a minute. What if we don't always want to be on this line? What if we want to be able to move up and down? We want to move in 2 dimensions. Well, what's the next letter in the alphabet after x? Y. Okay? So they put 2 number lines next to each other. And there you go. Okay? All right. So the next thing we want to talk about is we want to talk about how to find the distance between 2 points. Does anybody know the distance formula just off the top of their head? Distance formula? Distance between 2 points. Anybody know what it is? Got Sven, he's got his hand like most of the way up. Lynn's got it up. Okay, got a couple people. Okay. Logan, what is it?
It's the square root.
Big square root. Whoops. Hold on 1 second. See what's going on here. Let me let this restart. My pen wasn't working there for a second. Okay, so you said a big square root and then what?
X2 minus X1. Absolute value.
Absolute value? Okay. But we'll do parentheses and then what?
And then plus parentheses Y2 minus Y1.
Okay. Almost. Very good. Okay. What do we need on there?
Squared.
Each one of these needs to be squared. And we could have done absolute value and then squared it, okay? But we do need the square on there, and let me show you why. So let's take a look at this diagram right here. I have two generic points. I call one of them x1, y1, and the other one x2, y2. Why do we have those subscripts on there? Because there's two of them. I need to be able to tell them apart. It wouldn't do me any good if I wrote this one as xy and that one as xy. I wouldn't be able to tell them apart. So literally those subscripts, those little numbers that are written down below, okay, just mean this is the first xy pair and this is the second xy pair, okay? So this represents two generic points. They could be anywhere. They could be in quadrant 1 and 4, 3 and 2, whatever it happens to be, okay? So any two generic points. And we want to find the distance between the two of those. And the way we do that is we make this right triangle right here. And if this is x1 and this is, if I follow this x coordinate straight down, this is x2. So my question for you is, how far is it from here to here? From this point right here to that point right there on the right triangle? How far is it from here to here? Let's say this number was 2 and this number was 10. How far is it? It's 8. How did you get that? Subtraction, right? You subtracted the left one from the right one. So it's right minus left. So this is going to be x2 minus x1. That's that entire quantity. Okay? Everybody watch. Follow this one over right here. This y coordinate is y1. Follow this one over. This y coordinate is y2. And the question is, how far is it from here to here? From this point to that point? Again, if this were 6 and this was 2, what would the difference between the two of those be? How far would it be between those points? It would be 4. You do that by subtraction. Here we did right minus left. Here we're going to do top minus bottom. So this is going to be y2 minus y1. Now, if I left that diagram, and you guys have all had a decent amount of geometry, haven't you? This is x2 minus x1, and this is y2 minus y1. And I said, I want to know this side right here. There's a formula that relates this leg, and that hypotenuse of a right triangle. What's it called? Okay, so a squared plus b squared equals c squared is what we're after. It's called the Pythagorean Theorem. Okay, so if I take this leg and square it, so if I take x2 minus x1 and I square that, and then I take the other leg, y2 minus y1, and I square that, it should equal the distance squared, the distance between those 2 points, that side of the right triangle, the hypotenuse. Well, what if I don't want d? Or sorry, what if I don't want d squared? What if I just want a plain old d? Take the square root. Now, we put a square root in the problem. Why don't we have to do the plus or the minus? Because it's distance, and distance is always positive. Okay? That's where that formula comes from. Now, having gone over that, how many of you have seen the distance formula before? Okay, good. All right. All right, then another one that we'll just throw in. Does anybody know what the midpoint formula is? Tammy? Very good. Okay. Okay, so I'm just going to add the two of them together and divide by 2. The two x coordinates and the two y coordinates, and divide by 2. So this is the midpoint formula, and this right here is the distance formula. Now, when somebody says midpoint, think average point. And how do you average two things? You add them together and you divide by 2. So you're literally finding the average point, the point in the middle. Okay? It's one of the few formulas where you add the two coordinates. The rest of the time, like with slope and stuff like that, we subtract them. Any questions? Okay, then let's find the distance between these 2 points, and then it says find the midpoint also. Definitely the easier of the two is the midpoint, so I'm going to do that right here. The midpoint would be 0 plus 1 divided by 2, and then -5 plus -2 divided by 2. So the easiest way to write that is going to be, we're going to write that as 1/2, and then I'm going to write -7/2. And remember, once you get past pre-algebra, we usually don't write things as mixed numbers. We're going to leave that as -7/2. We're not going to write -3.5 or -3.5. We're going to leave it as -7/2. Okay, now let's find the distance. The distance between the two of those is going to be the difference in the x coordinates. So I'm going to do 1, okay, and do yourself a favor, everybody listen please. This is x2, y2, and this is x1, y1. Write down x2, write the minus that's part of the formula, and then go find out what the x1 is. That's a 0, quantity squared. Then we're going to do the same thing here. Y2 is -2. Write the minus that's part of the formula, and then go find y1. What is y1? -5. Now, here's a common mistake. We talked about common mistakes the last couple of days. Everybody watch, please. A common mistake is for somebody to say, oh, there's already a minus. I don't need to write it again. Is that true? Nope. Okay, so I want to write a -5 quantity squared. What does that -5 turn into? That turns into a +5. So here's what we get. This is 1 squared. This is going to be 3 squared. Right? So I end up with the square root of 1 plus 9, which is radical 10. Now, that's the exact answer. If we came up with a decimal approximation, we'd have to throw that in the calculator. Okay? Anybody got a calculator handy? Go ahead and throw in radical 10. We're expecting something that's a little bit more than 3. Okay? Why has it got to be a little more than 3? Square root of 9 is 3. Okay? It's a little bit more than the perfect square just before it. So what is the answer there, Logan? 3.16. Okay? So there's the exact answer, and there's a decimal approximation. Okay? And then again, I'm just going to set this one up in both cases. Well, let's go ahead and find the distance. So I'm going to change colors here. Distance is big square root. I'm going to do -3, and then what? Minus -1. So I'm just going to write +1, quantity squared. -5 plus 4, quantity squared. So here's what we get. This is going to be -2 squared. This is going to be -1 squared. So I end up with radical 5. Okay, that would be the distance between the two of them. Again, if I were doing a problem and I ended up with something like this. So let's say I solved a problem and I got this, radical 18. Would I leave it like that? Nope. We're going to write that as, factor it, 2 times 3 times 3, 2 3s. So 3 radical 2 is how you do that. Okay. And again, depending on the situation, if it asked for it or it were a story problem or something like that, you might want to get a decimal approximation, but generally speaking, exact answers are better than decimal approximations. Okay? And then again, we'll average the two of these to find the midpoint. Midpoint on this one isn't too terribly bad because it's just negative, whoops, I'll do a -1 minus 3 over 2, and then -4 minus 5 over 2. So this is going to be -4 over 2, -2, and this is going to be -9 over 2, which we're just going to leave as -9 halves. So there's our distance and there's our midpoint. Any questions? Okay, raise your hand if you've seen the midpoint formula before. Okay, good. Okay, so let's change gears just a little bit. Let's talk about scatter plots. So we're actually going to plot some data. Can anybody tell us what a scatter plot is? Just ballpark, anything close. Do you know what a scatter plot is? Noah?
Isn't it a kind of line graph where you try to find correlations?
Okay. A lot of times on a scatter plot, we'll have the points kind of line up and we'll come up with it's called a linear regression. We'll try and estimate what the line would be that would go through there. It's usually not perfect though, right? Okay. Hop, can you add anything to that? Yeah, so the points are random everywhere. What we're going to do is we're going to take data, and plot on X, Y axes. Now, a couple things that we've got to be careful with. You'll notice that I've got a problem right here. I just copied this out of the book. No graph over here. One of the hard things about doing scatter plots is how do you label and how do you set up the graph so that somebody could understand it? Because if you don't do it right, your graph could be pretty misleading. Okay? If you look in magazines and newspapers a lot of times, the graphs aren't done very well and they can really mislead what your opinion should be or what the information should be that you should take from that graph. So on this one right here, it says the table shows the number Y. So they've already assigned variables for us, Y, of Walmart stores for each year X, 1992 through 1999. Okay. Now, usually what we do is we say X is what we call the independent variable and Y is the dependent variable. So Y usually depends on X. You plug in an X, you get out a Y. And in this case, it makes a little bit more sense to say, you know, we're going to say what year it is. That's going to be the X, and then we'll tell you how many Walmart stores there were then, okay? Rather than the other way around. We'll tell you how many Walmart stores there are, and then figure out what year it was, okay? See how that setup makes a little bit more sense? So we're going to draw a set of axes right here. And I'm going to put the x-axis here, and we're going to label what that is. Because it's important when you graph stuff and when you're representing things that people are able to interpret that. That's going to be in years, okay? What year it is. And then up here, this is going to be the y-axis, and that's going to be the number of stores. Okay, now, normally, what does this point right here represent? What did you call it again, Tony? The origin. Usually that's 0, 0, right? Okay. Now, there's not a problem with making it something else, but you should definitely tell people that. And one thing that we could do to make this a little bit better is because on this axis, we're going to start right here at 1992, okay? That little squiggly right there lets people know, hey, this didn't start at 0, okay? Now, that's not a big deal on this particular one, okay? But it would be a nice thing if we put that down there. And then let's do this. This is going to be 1993, and I'm just going to put an apostrophe 93. And then we're going to try and equally space them out. And before I do that, everybody look, please. Let's look through here and make sure they didn't skip anything, because sometimes data will skip from year to year, or maybe they measured it every 2 years and then maybe every 3 years or something like that. Do I have them all represented every consecutive year, 92 through 99? I do. So we're going to go through here. Here's 94. Here's 95. And again, one thing that I've noticed, and this would be a huge pet peeve of a lot of math teachers, is when students label their axes, they don't make it anything near uniform. Okay? It's hard to tell, you know, how big the distances are. Notice how each one of those, I mean, this is just done by hand, so it's not going to be perfect, but that looks pretty good. They're all equally spaced for 1 year increments. Okay, now, the first bit of data is 2,136 stores. Walmart is gigantic, even back then. Okay? Did anybody know they normally bring in $1 billion every day? $1 billion every single day. Okay? All right, so we're 2136, and then let's look at what happens. It goes up and up and up and up. Okay, we've got to end at about 3,800. So if we're going to roughly scale this so that it looks right, okay, we're going to want a scale that goes from about maybe 2,000 all the way up to about 4,000. So before we just blindly go through here and just start marking our axes, okay, let's first of all break that just a little bit and go like this. And let's put 2,000 right here. Now, if I were scrunched down a lot, or maybe I had tons of space, let's go up to the very top. And what are we going to put at the very top? We're going to put 4,000. Okay? Let's stop right there for just a second. What we've done right here, we haven't graphed anything. And this is probably the most important thing you could do here. There are a lot of students that can't set up a graph like this and can't make it so you can read all the data off there and so that it looks nice. So if you've got data and you're asked to make a scatter plot or graph it, you should plan out how you're going to do that before you even start. Because plotting the points is the easiest part, setting it up is the hardest part. Okay? Does everybody see how this is going to be a breeze now? All I need to do is go through each one of those 8 data points and plot them. So this first one is 1992 and 2136. So we're going to find 1992. Probably ought to mark 3,000 in the middle there. And maybe if it was helpful, we could mark where 2,500 is. So we're going to put the point about right there. One thing that can be helpful if you're graphing data is if you have to use it again, you could actually write the value right there. We're never going to be able to tell exactly where that is by looking at it. If we write the point next to it, then that's pretty good. We've got the data over here, so that's not as big a deal on this one, and I'm not going to do it for the rest of the points. But realize if you did need that, if you wanted all the information on here, you could just at each one of those data points, you could put what it is. It's pretty clear it's at 1992 in the X. We'd want to be more clear that it's at 2136 in the Y. So the next one is 2440. And then we continue going up. We're at about 2759, just shy of 3,000 right here. And then I've got 3054 at 1996, 3400 in 1997, 1998 we're at 36 something, and then 99, 3815. So we're about right there. Okay. Now, on this graph with the scale we used, Noah, what do these look like?
Looks like a line.
They look like a line, okay? Could we find the slope? Could we find the y-intercept, which represents the number of stores, all that sort of stuff? Probably could do that. Not important here, don't have to do that. Just need to understand what a scatter plot is. Okay, are there any questions? Okay, if you didn't learn anything else from this problem, if all of that was new, just make sure you're aware, before you plot something, plan out how you're going to draw your axes. That's a really important skill. Okay? That will set you apart from other people in the future. Okay, so the next thing we're going to do is we're going to do something called transforming points on a graph, or transforming a graph. Okay, that also is a really good skill to have. There are lots of ways that we can transform points. Okay, the simplest one is called a translation. Okay? A translation is where we take all the points and simply slide, or we could say move if you wanted to. Move all the points on the plane around the same amount in the same direction, so we end up with the same shape, just in a new location. Okay, and most of the time in even a basic geometry class, you end up doing some sort of translations. Okay? So, example number 8, this is out of the textbook. I actually copied this graph and then got rid of the triangle. So here's what we want to do. It tells you where the vertices are. It gives you the x and y coordinates for each one of these vertices. It also labels them on the graph. Then it says shift, and shift is another word for a translation. So if I say a horizontal shift, okay, this vocabulary is going to come back, so please watch. If I say horizontal shift, that means a shift left or right. If we say a vertical shift, that's going to be a shift up or down, okay? Horizontal is in the X direction. Vertical shifts are in the Y direction, okay? So we want to take the triangle and we want to move it 3 units to the right and 2 units up. Now, here's the interesting part. We could do this as 2 separate moves. We could take this and slide each one of these 3 units to the right. 1, 2, 3, and put that point there. 1, 2, 3, put that point there. And 1, 2, 3, put that point there. You'll notice that what I've got here is an exact copy. It's a congruent figure. It's just in a different place. And I could figure out what the coordinates are. Now, if all I do is slide it to the right, which coordinate changes? Is it the X coordinate or the Y coordinate? Only the X coordinate, okay? If all I do is slide it to the right, the only thing that changes is the X coordinate. So you'll notice that this point right here still has a Y coordinate of 2. It's just that the X coordinate changed. Same thing with this one. Still has a Y coordinate of 3. It's the X coordinate that changed. So horizontal changes change the X coordinate. Vertical changes change the Y coordinate. And we have both of those in this particular case. So now all I need to do is slide this one up 2 units. So we'll go up 2, and up 2. Okay? And there's the shape that I'm after. Now, that's done in 2 separate moves. Slide to the right and then slide up. I could do this. I could just do the whole thing at the same time. What would happen to this point right here if I moved it right 3 and up 2? Yep. Add 3 to the X. That's going to be 2. And add 2 to this. That's going to be 4. So let's come over here and find 2, 4. So 2, 4 is right there. If I take the point 2, 3 and I slide it to the right 3 and up 2, that's going to make this 5, and that's going to make that 5. So we'll go to the point 5, 5. And if I slide this one to the right 3, we're going to add 3 to that, so that's going to be 4. Up 2 from negative 4. If I go up 2 from negative 4, where am I? Negative 2. So over 4 and down 2. And there it is. Okay? So this one was 2, 4, 5, 5, 4, negative 2. Exact same shape. Notice that it looks just like the blue one that we did in 2 moves rather than just 1. Okay? Same shape as we started out originally. It's just moved to the right, 3, and up 2. Any questions there? Okay, raise your hand if you've seen translations before, slides. Excellent. This ought to be really easy. Okay, there are some other transformations that we ought to be familiar with. Okay, and these are the basic ones, and these are going to get us ready for some stuff that we're going to cover in chapter 1. Okay, so pay close attention to this. This one says we've got the original point, and then the transformed point is negative x comma y. So I'm going to graph this one in, let's do red here, let's do blue here, and let's do green here. Okay. Anybody know what we'd do with this? What does that look like? Very good. It's called a reflection. Okay. Now, if you can't see that that's going to be a reflection, one thing that you could do, and remember this is what students who are good at math, if it looks confusing to figure it out with variables, let's pick some numbers. So let's say I picked the point 2, 3. If I came over here and graphed 2, 3 right here, if my point here numerically is 2, 3, what would it be right here? Negative 2, 3. So back 2 and up 3. It has the same y coordinate, it just has a different x coordinate. Instead of going to the right, we went to the left. Good with that? Lynn, what did you call this? Okay, this is called a reflection. Okay, this is called a reflection across what? across the y-axis. Now, that seems a little bit strange that the x-coordinate changes and yet it's called a reflection across the y-axis. If you think about it, that makes sense. The y is the border between the right side of the x-axis and the left side of the x-axis. Okay? So all we're doing is we're trading right for left and left for right. Okay, let me show you one more example. Let's say I did -2, let's do -3, -4. So -3, -4 would be right here. What would it be if I transformed that point? It would be 3, -4. Notice that only the x-coordinate changes. So that would be 3, -4. We're right here. They are reflections across the line y equals x. Okay, another name for this type of symmetry, this would be called line symmetry or fold symmetry. If we folded it along that line right here, the left would look the same as the right. Okay, so that's called reflection across the y-axis. Okay, let's take a look at the next one. Oop, I did that one in green, didn't I? We'll go that way. Okay, so what if we have a point xy and then I do -x, -y? Start with xy, do -x, -y. Close. It's not quite a reflection. This one's a little bit different. Let's do a number example. Okay, let's take that same point 2, 3. What would it be now? -2, -3. So let's see where it ends up. 2, 3, -2, -3. Ends up right here. This one's a little tougher. Let's do another one. Okay. Let's do -1, 4. Where would -1, 4 end up? 1, -4. So -1 and 4 would end up at 1, -4. Okay? You know what this one is? Like, not a reflection over the origin. Okay? What it's called is symmetry with origin. Okay? Or another way we could describe this, this is rotational symmetry with the origin. So what this means is when we say rotational symmetry, or sometimes this is also called point symmetry, instead of being reflected or having symmetry along a line, this is symmetric around a point. So if you put your pencil, and go ahead and do this, put your pencil right on the origin, and then turn your paper 180 degrees. Everybody do that. Put your pencil on the origin, turn your paper 180 degrees, so it's going to be completely upside down. Okay, now, take your pencil off there, once you get it upside down, and compare it with my graph that didn't turn anywhere. Doesn't your graph look exactly the same? Okay, so that's what symmetry with the origin means. It means if we turn it 180 degrees around the origin, the graph looks exactly the same. The graph looks exactly the same. So again, we've got reflective symmetry, line symmetry with the y-axis, just the x-coordinate changes here, right? Changes for left. Okay. With this, if we change the sign of both of the coordinates, we get what we call rotational symmetry or symmetry with the origin. Okay? I take quadrant 1, slide it over here in quadrant 4. Take quadrant 2, slide it over here in quadrant 1 and 3, quadrant 2 and 4. Okay? All right, and then let's take a look at this one right here. I'll switch colors. Now, what would you guess this one's going to be? Okay. So this one is going to be a reflection across the x-axis. If this first one right here was reflecting right for left, switching the left and the right side, look at what happens here. Let's take that same point 2, 3. It's going to be 2, -3. So 2, 3, 2, -3. What we're doing here is not changing left for right. We're changing top for bottom there, okay? Any questions? Okay, let's come back up here. I'm going to go green on this one. Okay, let's do a reflection across the x-axis. Which coordinate changes if we reflect that triangle, the original triangle here, across the x-axis? Which coordinate changes? What is it, Tony? It's the y. Remember, it's a little bit backwards. If we're symmetric with the y-axis, it's the x-coordinate changes. If we're symmetric with the x-axis, it's the y-coordinate that changes. So all I need to do with each one of these is change the y-coordinate. So this is going to be -1, -2. This is going to be 2, -3. This is going to be 1, +4. And can you see the symmetry? Can you see that we switched top for bottom? And if we made this symmetric across the y-axis, which coordinates would change? The x-coordinates would change. So this would be 1, 2, -2, 3, and this would be -1, -4. Okay, can you see that that is a reflection across the y-axis for the original one? Okay, and then you might play around with it. If we switch both coordinates, it would take that and it would rotate it around the origin. Okay, so one thing that might be kind of fun is, what if you took a couple of points here, what if we made our own triangle? So this point right here is 3, 0. This point is 5, 2. And this point right here is 2, 4. What if you took that one and you made copies of that, different colors or whatever, okay? Made it reflective across the x-axis, the y-axis, and the origin. You'd be able to see a copy of this one with all three of those types of symmetry, okay? Go ahead and do that with this triangle right now. Check with your neighbor before you leave. And that's it for the prerequisite chapter. Review tomorrow. Come with questions. Test on Monday and Tuesday. I'm looking for awesome scores. That would be great if everybody got 100 or 95 or something like that. Is that what it looks like? Okay. And look at these points. Notice how each one of them changed. How is this one symmetric? The blue one. Symmetric with the origin, okay, because both of them changed. What about this one? Symmetric with y-axis. Remember, trading right for left. Okay, symmetric with the y-axis. The x-coordinate changes, so symmetric with the y-axis. And this one is symmetric with the x-axis, trading top for bottom. Okay, can anybody think of a different way to think of symmetry with the origin? What if you did two reflections? What if I reflect it across the x-axis, then across the y-axis? Do I get this right here? I do. Okay, so you can do 2 reflections and you get 1 rotation if you do it the right way. Okay, please come tomorrow with questions. I'm looking forward to a whole bunch of questions. We'll do as much as we can. I want to make sure that you feel ready and prepared for that test on Monday. Again, know the stuff that we talked about in lectures. Know the stuff that we went over as examples. Okay? Do the review assignment so you know what questions you have tomorrow. Okay? P.8 ought to be pretty easy. There aren't a ton of problems and it's just graphing some stuff. Okay? Have a great day.